All right, let's do the last part of the notes for phase changes. And phase changes occur when a substance changes from one state to another. So we're talking about things like melting, freezing, vaporization, condensation. There's also sublimation and deposition, but we won't be doing that as much because we're going to be calculating the energy changes that are happening whenever we're either going one direction or the other. Melting or freezing, same point, it's happening at the same point, but it's just depending on which direction you're going. And recall from the beginning of the year that phase changes are in fact physical changes, so make sure you keep that in mind. All right, let's move on to the next slide. All right, so let's look at this heating curve. It is the heating curve for water, and let's spend a few minutes talking about this so we can kind of see what's going on. And what this heating curve shows is it shows down here from A, which would be well below freezing, heating this up all the way through F, which would be, of course, vaporization or steam. And so we have these areas where we have flat lines right here from B to C and D to E, and that is actually where phase change is happening. So in this case, when we're heating it up, it's where we go from ice to water, so we would be melting it. And then we continue to heat it up, and then we get to D to E, and then we're having phase change from where it's changing from liquid to water vapor or steam. Okay, and of course I'm sure that you notice that during this time from B to C and D to E, when phase change is actually occurring, the temperature remains constant. We do not have a temperature change during that time frame. And because of that, what's actually changing in terms of energy is potential energy. So as we heat it up and we're continuing to add energy into the system, but while we're at phase change, it's only the potential energy that is increasing. However, when you're in these sloped lines going up, and again from E to F, during that time, as you can see, the temperature is changing. And so since the temperature is changing, in that time on the graph, the kinetic energy is increasing during all of those. Kinetic energy increasing and kinetic energy increasing. Okay, so let's move on to the next slide and continue to discuss what's going on. Hopefully you understand this. If you don't, make sure you ask questions in class. So I'm sure you noticed that on the heating curve, the temperature rises very quickly when the solid or liquid or the gas is being heated. So those slopes of those lines were very sharp. The higher the specific heat of the substance, the shallower the lines are on the heating curve. And of course that indicates that the stronger the interparticle forces. The higher the enthalpy of change, which we're going to talk about heat of vaporization or fusion in a moment, the longer the phase change time takes. So let's move on to the next slide. At phase change, the temperature of the substance does not change. We saw that in the graph. And that's because during that time, all the energy is being used to break apart the intermolecular forces that are holding that phase together. For instance, when you are talking about water, you've got hydrogen bonding that's occurring, and so it's going to take longer to break those forces. So remember we said all the energy change was potential, not kinetic. And then the stronger the IMFs, or the intermolecular forces, that longer that phase change takes place. So how do we calculate those energy changes? Well, it depends on if it has a phase change occurring or not. If it does not have a phase change, then without phase change, we're going to use that regular MCAT formula that we've been using. Same thing, specific heat of the substance, mass, T final minus T initial, just like what we did in the beginning of the notes. So that's going to look the same if there is not a phase change occurring. So this is just like what we did earlier in the notes. So I want you to pause the video and work out the problem and see if you get, first of all, the answer that was listed on the paper, but also if your work looks like my work. So how'd you do? So hopefully you got 78,400 joules. So remember this number because we're going to be using this in a second as we continue to calculate for a phase change. All right, but what if our temperature changes does include a phase change? Well, then we have to use either the heat of vaporization or the heat of fusion. Sometimes we have to use both because we might be going from a solid all the way to a gas, and we would have to use both. But we would be using vaporization if we were at the condensation vaporization point, and that is the heat required to vaporize 1 gram of liquid is its heat of vaporization. If we were at the melting freezing point, we would be using the heat of fusion, and the heat is required to melt 1 gram of a solid is called its heat of fusion. I know it seems weird, melting is called heat of fusion, but remember the opposite of melting is freezing, which we would be fusing the particles together to make a solid. So let's see how we use these. So if we're at phase changes, this is the formula we would be using. We would be using Q is equal to delta H of the change. That change is either going to be vaporization or fusion times the mass. Okay, and so let's go on to the next slide because it's very... So here again is the formula. At phase change, you would use Q is equal to the mass times the delta H of either fusion or vaporization. Since there is no temperature change at phase change, you'll notice that there is not a temperature included in this equation. So let's move on and do an example calculation. So here we have how much heat is needed to change 250 grams of liquid water into steam at 100 degrees Celsius. So we are obviously at phase change and we are at the vaporization. So we're going to need the heat of vaporization. And so that is something we can look up, and I will give you that value. The heat of vaporization is 2,260 joules per gram. So it takes that many joules to heat up 1 gram of water. So now we're going to plug that into our equation. So we're going to use Q is equal to M times delta H of vaporization. So it would be 250 grams, and then we would multiply that times the 2260 heat or vaporization joules per gram, and then you'll see our grams cancel, and so we are left with an answer of 565,000 joules. And then of course if we wanted to put that in the correct number of significant figures, which in this case is going to be 4, we would write that as 5.650 times 10 to the 5th joules is how we would record that correctly. All right, so let's put this all together. Energy changes of a heating curve. To find the energy changes, you're simply going to add up the value for each change and the value at phase change until you've calculated all the parts that you need. Now, we've already done this in our previous 2 slides, but if we were going to do this, we would say Q total is equal to Q1 plus Q2 in this case. So we calculated this on the very first slide we did on this lesson. We calculated the change from 25 to 100, and we found it to be 784,000 joules. And then on the previous slide, we calculated how much energy is used at phase change, and we got 565,000 joules. And so we add that up, and we get a value of 643,400 joules. And so that would be our answer to this question of what is the heat needed to raise 250 grams of water from 25 to 0 degrees Celsius. All right, so back to that heating curve review. Here's what you would use at each one of these positions of the graph if you were trying to figure out how much energy was required for the phase change. If you're at A, then you would be, from right here, you would use the Q is equal to M, the specific heat of the solid, times the temperature. When you're at the phase change of melting or freezing, you would use Q is equal to M, mass, times the heat of fusion. When you go from B to C, when you are heating it up from a liquid to getting to the boiling point, you would use the Q is equal to M times the specific heat of the liquid times delta T. And then, of course, at this phase change, you would use Q is equal to M times the delta H of vaporization. And then lastly, if you were above the vaporization point, you would use that Q is equal to the mass times the specific heat of a gas and times the delta T. In the case of water, which we've been talking about, the specific heat is different for a solid, water than it is for liquid water than it is for steam water. So you would have to use those values. You can't use the same specific heat values for all three of those. You have to use the one that is specific to its state of matter. And so the state of matter would be very important when you're doing these calculations. If you are having trouble understanding this, or you need to ask questions, you need to make sure you ask these questions in class so we can get that clarified. All right, as promised, stay tuned on the next slide for jokes. All right, this is a shout out to my 6th period. You know, my favorite one and only pre-AP class, my 6th period. So here's joke number 1. Where does light end up if it's bad? In a prism. What is the dullest element? Thorium. All right, one more. What do you call a bear with no teeth? A gummy bear. All right, see y'all next time. Bye.